Hello, our third lecture this week is about errors in experiments. We're going to cover random and systematic errors, significant figures, accuracy and precision, dealing with errors in labs, and accuracy of the mean. Okay, random errors. We're doing experiments. Normally you'd be doing experiments in labs by now, and you'd be trying to work out conclusions from the measurements that you take. Obviously you want your measurements to be as accurate as possible and precise as possible. We're going to look at exactly what that means. This lecture course is looking at probabilities, statistics, and a lot of that comes down to errors in data, which mean that we can never quite measure what we want. We get spreads of data and we're trying to interpret that to find reliable mean values and to understand the nature of the distributions that we're measuring. So let's understand what causes the distribution. Random errors are the things that happen which affect our experimental results and which happen randomly. They happen by chance, and they will be different each time we do an experiment. If we take an example of using a balance, a random error could be just the precise position that we put our object on the balance. Each slightly different position of the object will give rise to a slightly different measurement of its mass. When it comes to measuring a liquid in a measuring cylinder, the point of view at which you look at that meniscus from will affect your interpretation of what the level is, and each time you look at it, it will be from a slightly different position and you'd see a slightly different value. Any environmental changes on your system will affect what its measurement is. So on a balance, if you're trying to measure a sensitive small amount, a breeze, a draft onto the balance will affect its measurement, and that will change from time to time in a random way. Likewise, if you're trying to measure the height of somebody, the exact posture that they take will affect the height that you're measuring. So all of these things we say are random, they're subject to chance, and each time you take the measurement it will give rise to a slightly different error in your measurement. The other main type of error we need to be concerned with is systematic errors, and this is where there's an error in your measurement but it's not different each time. There's a consistent reason for that error which will give rise to a pattern in the error in your data. So it could be as simple as not tearing a balance before you take a measurement. So that means all of your measurements are offset by a certain amount, in this case 0.02 kilograms. If that balance wasn't teared, all of the measurements would be offset by that amount. So they all have an error and they all have the same absolute error. It doesn't always have to be the same amount. For example, take this ruler. We're using the ruler to measure the length of this object. Well, this is a metal ruler, and if the temperature drops, the ruler will shrink a little bit due to the contraction of the metal ruler, and therefore you'd measure a different length of the object which hasn't changed length. So in that case the error is not always the same. The error is dependent on the temperature. It's a systematic error because there's a repeatable systematic way in which the error changes with that condition. So it's not always the same value, but there is a systematic pattern in it. And often this would be seen in data as drift in a parameter. So this instrument here is measuring the concentration of carbon monoxide in parts per billion in a gas, and you can see that measurement over time. And the gas isn't changing in this example, but the signal is changing. There's a bit of drift, there's a bit of variation up and down. So that might be a random error, or it might be other effects, but you can see there's a consistent change in the signal over time. That's what we would call drift, and perhaps it is the temperature of the instrument changing over time, or some other environmental factor that changes over time. And it shows a systematic error where there's a pattern in how that error is changing over time. So we've got two principal sorts of error. Any experiment you're designing, of course you want to minimize these and eliminate them where you can. Systematic errors are typically things that we can account for, and things that if we identify them we can either eliminate them or we can treat our data to accommodate what's happened. When it comes to data that you're handling or results that you're reporting, you need to be careful and thoughtful about the significant figures and the precision of that data. There are two rules: no measurement is completely accurate, and no measurement is complete without an indication of error. So what does that mean? If the length of an object is 0.428 meters, reporting the length in that manner, it implies that the accuracy is about 0.001 meters. So the number of significant figures that you use to write down a quantity, it implies to the reader what the accuracy of that reading is. If you recorded it as 0.4 meters, it would imply that the length is only known to 0.1 meters. And that's probably not true, because you've probably got a tape measure or a ruler which is accurate to within a millimetre or a few millimetres. If you recorded it as 0.428196667 metres, that implies that that quantity is known to 10 to the minus 8 metres, and that's extremely unlikely. And so when you're recording or reporting a measurement, you're implying to the reader what the accuracy of that is. And that's why significant figures, or one reason why significant figures are important, because you're telling the reader implicitly within that something about the quality of that data, what the accuracy of that data is. So precision, this implies a lot of precision, but it's not accurate. This one implies that there's has not very much precision, and it implies that your measurement is not as accurate as it actually is. So there's a balance, you see, between precision and accuracy, and it's your responsibility to do that. When we do exam marking, when we look at your lab reports, we take these factors into account. We expect you as engineers to start thinking like a professional and thinking about how many significant figures you report your data to. And picking a suitable number of significant figures indicates to us that you're being thoughtful about the accuracy of your data and reporting it in a reasonable way. When it comes to reporting error, there are two main ways it gets reported. Absolute error, and so that might be like this: 0.428 plus or minus 0.002 meters. So this is an error, and it's an absolute error because it's telling you exactly what that is and what its units are. The other way you often find it is relative error, whereby you take the absolute error and divide it by the quantity, and in this case you'd say there's a relative error of 0.47%. So both of those are common ways in which error is reported. And what we're seeing through this is that readability is not the same as accuracy. The precision of a measurement is not necessarily the same as what your instrument is reading out. So a simple example of this is with a thermometer, and you'll find this routinely with thermometers if you ever need to work with them. The readability of a thermometer is typically more precise than the actual accuracy of the thermometer. You have to pay a lot of money to get a thermometer which is accurate as its readability implies. So here's an example from a reputable supplier. It costs £120 before VAT, so it's not cheap, and it has a display which tells you the temperature to the nearest tenth of a degree C. Okay, so you think that then it might be accurate to that much. That's what it's implying. That's what we're saying. It's implying that it has an accuracy to that degree of precision. But take a look at the manual that comes with it. The specifications tell us that the best accuracy for this thermometer is plus or minus 0.3%. So it's giving us the error in terms of a relative error. So if we consider what that means, the readability or the resolution of our thermometer is 0.1 degrees. But with a relative error of 0.3%, if we take that relative error of our quantity we can see on the display, 187.5, you see that equates to plus or minus 0.6 degrees C. So by looking at the spec, we see that actually the accuracy of this instrument is not as good as the readability implies it is. So if you're trying to do careful experiments in your career, it's important to take note of this, and likewise when you're presenting your own data, you don't want to be doing this trick of making your data look more accurate than it actually is. So this is an aside. When it comes to acting as a professional, as an engineer, and looking like you know what you're doing, this is a handy website from the US National Institution of Standards, which gives lots of useful tips on how to report data in the sort of international conventional notation. And here's an example of how to report with a few tips. This is the top one is the right way of doing it, and the bottom way contains some mistakes. So the convention is that units are not italicized. This helps us to identify what's a unit and what's a variable parameter. So that should be not italicized. Likewise here, time t is a variable parameter representing a number, and so that one should be italicized. Likewise, capital T, that's another parameter representing a number, so that should be italicized. And you'll find lots of information there about how to present your results in the professional way and to make them look good. Okay, so here's another example of an instrument. It's a weighing balance, a mass balance. And again, we want to take an example of looking at accuracy and precision and understanding what the manufacturer's manual tells us about it and seeing what some of the errors can be. So this is the balance. This is from its manual. We select the particular model we're looking at, and it gives us information about the accuracy in terms of linearity. And it says the linearity is plus or minus 0.002 grams. What does that mean, and how does that affect our results? So what we're going to watch is this video which shows the process of calibrating an instrument, or in this case we're just going to check how accurate it is and how linear it is. So I'm going to play the video. Here we go. And it's a process of putting known masses onto the instrument and taking them off and putting them on again. And you can see on the display what the instrument's recording. So the instrument has a display of 3 decimal places, so that's down to 1 milligram. So you can see if you're trying to weigh 200 grams and you're trying to measure with an accuracy of 1 milligram, that's a challenge. You're talking about 6 significant figures if you can achieve that. And what you can see is that the balance isn't always going back to 0, and it's not always matching the known masses. So we assume that the masses are what they're meant to be. You'd have paid a lot of money for those standard masses. So if we assume that the masses are what they're meant to be, we can take that data and look at it and work out how accurate that balance is and what this linearity means. Okay, so we saw that. So this is what is happening with the balance. So let me talk through this graph. This is a graph. It's got a weight on the bottom, a mass more correctly, and this is the known mass. So this is the mass that we put on the balance, and we're assuming that these are exactly correct. There's no error or negligible error. And then this is the displayed value. Now the dotted line here shows what would happen if the linearity was perfect and if there were no errors. These would match exactly, would correspond exactly. But what we have seen is that both of these problems are occurring, both the problems of sensitivity and linearity. So sensitivity means that there's an error offset here at the highest value, and you can see that this line is not quite straight. It's a bit curved, and that's what we mean by, or that's what's associated with linearity. So what we can do, if we're calibrating a balance, what you can do is you can take this highest mass and then you can reset the balance and tell the balance, well actually At this point we put 2 kilograms on it and it would shift its output to acknowledge that, and then it would say there's 2 kilograms on it. So you can always recalibrate a balance, and a balance like that would always have to be periodically calibrated to make sure that your results are within your desired accuracy. But even if it's calibrated and it's correct at its highest limit, if it's not quite straight, the response, if it's not quite linear, the response, there will still be errors along the way, and that's what's referred to as linearity. So in the manual, it's assuming that you can calibrate it correctly and that at its maximum range it would give you the right answer, the right value of reading of mass, but it's got some error in its linearity within that scale. It said it was 0.002 grams. So for our balance, the maximum difference between what would be the correct reading and the actual reading should be less than, no more than 0.002 grams. So we can look at our data. We know the mass that was put on the balance, and this works through the sequence of masses that were added and then removed, and we could see the reading on the balance that happened. So in this case we take the maximum value 300 and the reading was 300.008. So in this case it hasn't been calibrated quite right, and that calibration hasn't been done, but we can still see what the linearity would be. So first of all we can look at absolute error, so that's the difference between the known value and the read value in grams, and we know that we can calculate the relative error from that. The linearity error, so we've set that to be 0 at the highest value, and then we can see how much we're deviating away from that as we are at different points of the scale. The highest linearity error occurs at this point, where it's 0.0013. That might be a little confusing because we can see 50 grams here for the known mass, 50 grams here for the reading, but this is saying essentially that actually if that's the maximum reading at that mass, when you are at proportionally 50 grams of that, then this reading actually should be a bit higher than what it is, because it's 300.008 grams at this point. So this is under-representing the mass a little bit, if it was a straight line from 0 to here. And we can see that linearity is indeed within the spec that was in the manual. The spec said it should be no more than 0.002 grams, and all of our values are. So you can see some of the detailed considerations of accuracy and precision that we get on an instrument like this. The instrument is telling us the mass to 3 decimal places in this case, 1 milligram, which equates to this parameter, this point here. So obviously again the readability and the accuracy are not the same thing. The accuracy is within 0.002 grams according to the linearity, and we can see that the readability is 0.001 grams. So they're kind of similar, but it's not as accurate as the readout might leave you thinking. So of course it's only as accurate as the calibration as well, and so if it was not calibrated correctly, then again you won't be getting the accuracy that the readout implies. The other problem we saw on this balance was a hysteresis error. So that meant that it went up one way, but then when the masses were removed, you were left at the end with a non-zero readout. And so the reading as it was loaded was different from the reading as it was unloaded, and that's called hysteresis. So these are some specific examples of errors that occur with a balance, and you may or may not in your life have to deal with this degree of accuracy, but all of these points are true for any instrument or any transducer that is taking measurements of a system. And what we've been talking about is accuracy and precision. These are useful concepts to understand your data, and you always want to be representing your data in a reasonable way with regard to its accuracy and its precision. So this illustrates low accuracy and low precision. And the risk is that sometimes your data can have high precision but low accuracy. So your balance can be telling you the mass of something to 0.001 of a gram, and it might do that very repeatably, but it's not very accurate because there's an offset error or the calibration isn't correct. So a high precision of a readout doesn't mean that it's an accurate measurement. It's better to have high accuracy and lower precision. So here the darts are all centered around the bullseye. So there's accuracy, they're all within the vicinity of it. The precision's not great because they are scattered around it. But it does mean in that instance, if you throw enough darts and look at where they're tending to fall on average, you'd actually be able to find the precise position of the bullseye. And of course, in an ideal world, you have a high accuracy and high precision. So when you're doing labs or looking at data, you want to be able to identify your sources of error, and you want to be able to calculate the effects of your error on the final results and the processes. So you always want to do that. You always want to look at the instruments that you're using to measure and where the errors will be coming from within your experiment. And with respect to those, you need to quote errors correctly, estimate what they are, look at manuals where appropriate and find out what the technical specification is of the equipment you're using. But also don't neglect the unidentifiable sources of error. And often repeating an experiment multiple times will reveal that the spread of the data is much greater than the predicted error. If that's what you find, if when you repeat an experiment the difference in the results from one run to the other is larger than the predicted difference that you'd get from the accuracy of each of your individual measurements and so on, if you find that that's happening, then that means you haven't identified all the sources of error. And that's okay. Sometimes it's not practical to do that or not feasible to identify all the sources of error. But if that's what you find, then you need to take that into account, and instead of spending your time working on the particular sources of error that you have identified, you need to think about, well, how can I get enough data out of the experiment to come to some conclusions about its accuracy and repeatability from that. So when you're doing an experiment, don't rely just on your own analysis of the errors of the instruments and measurements and so on. Also, always repeat an experiment several times and look at the variation of the output from experiment to experiment and compare that to what your expected errors and variance would be from the measurement analysis. Okay, so reporting data, we said you need to report data with an indication of what its accuracy is. We said that the number of significant figures is important because that implies its accuracy, and better still, it's to be explicit what the uncertainty is. So here's an example. We have a mass. The observed value, the red value of the instrument, is 12.14286 grams, and we've calculated that there's an uncertainty of 0.07313 grams. So how should we go about reporting that? Here are some examples, and we want to choose the most appropriate one. So the first example is not appropriate because it's reporting this to 7 significant figures, suggesting that it's accurate down at this level here. This is 1/100th of a micron. Now we can see that we've calculated, or we've learnt from somewhere, that the uncertainty is of the order of 0.07 grams, so 70 milligrams. 0.07 is here. So there's no chance of these numbers here of having any significance to what the actual value is. It's only accurate to something like plus or minus 0.07 grams. And so these numbers are just noise, they're not relevant. And reporting them can only result in misleading the reader into the accuracy of what you've measured. There's no value in them and they don't mean anything. Okay, so you might then report the data like this. We've got all the significant figures from your measurement, and we've also got the uncertainty that we found out. And you might think that's the best way of doing it because, well, all of the numbers are being reported, all the information is being reported. And whilst that's true, it's also pointless and not as simple or as elegant as it could be, because we know that these numbers don't mean anything. If it's only accurate to plus or minus 0.07 grams, there's just no point reporting what these values are. And likewise, if it's only accurate to plus or minus 0.07 grams, again, this 0.13 milligrams here is also of no significance. Okay, so here's another instance. This is getting better. We've made an effort to report the accuracy in a reasonable way, and that looks pretty reasonable. But here we've reported this still to 5 significant figures, to the nearest milligram, and we're saying that the accuracy is only as good as plus or minus 70 milligrams. So there's still no justification for reporting that 3 there. That's too many significant figures for the accuracy of our measurement. The next example, again, we're getting better. The number of significant figures has been reduced to 3. Often 3 significance in engineering is sufficient and is typically representative of the accuracy of what you've been able to measure. But here the significant figures for the error or the uncertainty is only given as 1. It's been rounded up to the nearest 100 milligrams. And there's no reason for that. It's less than 1 significant figure. 1 significant figure would be 0.07 grams. And for no justification, it's been rounded up to 0.1 gram. So then the next one is better still. We've selected the number of significant figures for the main value as 12.14. So here at the second decimal place, that does correspond to the uncertainty. And so there's a justification for reporting that. It's plus or minus 0.07 around that value. And so that's meaningful. And 0.07 is a meaningful way to represent the uncertainty. Trouble is here, they forgot to put the units on. And no reading is meaningful without the units. So finally, we have the best way of presenting it. We have units represented, we've got a suitable number of significant figures given the known uncertainty, and we're reporting explicitly what that uncertainty is, again to a suitable number of significant figures. And so that's great. So if every student reported their data like that, we'd be happy academics. Okay, so finally we're going to take this to the example of the metal testing that we were doing in the earlier mini lectures, and looking at how can we improve the accuracy of our experiments. We talked about a limitation to how accurate we can make an experiment. We might have tried to analyse the errors, and we've come up with some known uncertainty from those errors, but still when we repeat the experiment from one run to another, there's a spread, and it might be a spread that's larger than what we could expect from our error analysis. So at that point, what can we do? How can we make our estimation of parameters more accurate without necessarily having to change the experiment? So this was our example. This showed one of the histograms that we looked at earlier, with the one with the larger number of intervals. And this was done for 14 experiments. We found the mean value of failure stress, and we found the standard deviation for the data set that we had. That's the non-biased standard deviation. Now, of course, if you do more experiments, you'd expect to have some better numbers. So this is the same situation, but now we've done 114 experiments. And if we look at the histogram, we can see that it looks like a smoother shape. We've got the fitted normal distribution to it, and as we go from one to the other, I think you'd probably agree that the apparent fit, the closeness between those two things, gets better for the case with more data points. And that's something that we would expect to happen. There's a theorem called the central limit theorem, and it tells us that if you have an occurrence which is subject to random errors, if you start adding up what those errors are, we find that they become normally distributed. The effect of them is normally distributed. And it doesn't matter what the source of the error is. It doesn't matter if the individual errors are not normally distributed themselves. They could be evenly distributed, like tossing a coin, or it could be some other distribution. But the effect on data when they start being added up collectively is that they are normally distributed. And what that means is that, first of all, there's a reason for why we'd expect a normal distribution to fit data that's subject to accumulated errors like that. And it means that we can reason that because we'd expect it to fit this shape, the more data we have, the better the fit should be. And what we can find is that the standard error of the mean follows a pattern like this. So this shows us the standard deviation of the mean. So the mean is our estimate of the mean of the population. So that's calculated by finding the mean of the values. So this is the mean of 114 values. And what we're trying to do is estimate what's the mean of the population that our samples came from. And the mean has an error associated with it. What's the certainty we have that that's what the mean is? As we do more experiments, we become more certain about that value. And the certainty of that mean is equal to the standard deviation of our sample that we have. So it's the standard deviation of 14 points, or here it's the standard deviation of the 114 points. This is our estimate of the standard deviation of the actual population. And the standard deviation of our estimate of the mean is equal to the standard deviation of our estimate of the population divided by the square root of the number of samples that we have. So obviously the more samples you have, the more this will go down, and the more confident we are of our estimation of the population mean. So we can see that here with 14 points, the standard deviation of our estimate of the mean was about 13 megapascals, which out of 870 is quite significant. And by increasing it to 114 values, we've reduced the uncertainty, we've reduced the standard deviation of our estimate of the mean to 4.8 megapascals. So by doing more experiments and taking advantage of the central limit theory, we get better, more accurate estimates of the mean. And then you can see through this as well that this also tells us, through the standard deviation term of our collection of samples, it tells us an estimate for the variation or the standard deviation of the population, and so we can see how much variation there would be. And that is what manifests itself as the errors accumulated through the process and the variation in the actual sample itself from one sample to another. All of those things are the accumulated errors of the process, and that's what we can measure with this technique. So here we've looked at some practicalities of experiments. We've seen that there are two types of errors in general, random and systematic, and we've seen how significant figures, accuracy and precision are all important for interpreting data correctly and reporting data correctly. We've looked a bit at how to deal with errors in labs at the instrument level, and also in terms of making sure that you do repeats and checking the variation from one run to another against your estimate of errors from the individual measurements. And then we've looked at the accuracy of the mean. We've seen how by taking lots of measurements you can come up with more confidence in your estimate of the mean of a population. And we've also seen that the summation of random errors will tend to create normal distributions. In the next lecture we're going to look further at this, and in particular we're going to look at the propagation of errors. So we talked here in this lecture about how do we work out the expected accuracy of a result given some known, that we know that each instrument and each measurement will have some errors. Here in the next lecture we're going to look specifically at how do we do the mathematics of predicting the accuracy of a result of something we've calculated from the individual measurements. So we're going to look in particular at the addition of two measured values, and then we're going to look at the general case. So if you have two measured values with known error and we do something to them, we add them together, we multiply them together, what's the error going to be in our calculated value? Thank you very much.